Welcome to another video. We are going to show that this integral is equal to the square root of pi. And if you remember in the last video, I did mention I used this, I didn't compute it because I didn't want us to deviate from the focus of the previous task that we were trying to complete. But now that I have the time, let's do this. This you have seen in statistics. You know that, yeah, the one you see here. Yes, so this is the function that is integrated, or a modified version of it, this one. A little bit modified, and that's how you get that. Let's get into the video. Because there is no regular way of doing this, if we stick to the traditional integration methods and techniques that we have, I'll have to do something new, which I introduced that's about 2 videos ago. And look at this video. If you check this out, then you see the explanation for why I am able to do what I'm about to do. So what I'm going to do is say that this integral, I'm going to say let I be equal to this integral from negative infinity to infinity of e to the negative x squared dx. When I do this, I'm going to get an actual number as my answer, okay? Because this is defined on the rectangular axis. But I can also change the letter that I'm using. I can use x, I can use y. Because if I flipped it to the y-axis, I'll get the same area under the curve. So I could as well say, and let I be also equal to the integral from negative infinity to infinity of e to the negative y squared dy. So if I was given this problem and I integrate it, I would get an answer, which I call I. If this was the variable I was given also, I'll get the same answer. So what can I do? Well, I can multiply these two together and get something. Remember, math is all about manipulating what you have to get what you want. If I multiply these two together, I'm going to get I squared. If I multiply these two integrals, by the theorem I explained in the previous example, it's going to be just the integral from negative infinity to infinity. You repeat it. Then I'm going to multiply the two functions inside, which is e to the negative. If I have this, this is going to be this plus this. Negative this plus negative this is going to be negative x squared plus y squared. And it looks like I'm multiplying these two. It's going to be dx dy. This is what I squared is going to give me. This is what you call a double integral. Okay. I still don't know how to do this. Because typically when you integrate e to something, you need something beside it to take care of the derivative of the exponent. But now I don't have it. But there's something we know. Remember from our transition from rectangular coordinates to polar coordinates, that there's something that looks very familiar here. I can change x squared plus y squared to r squared. Okay, so you should recall, so let's do this. Recall that we can write x equals r cosine theta. We can write y equals r sine theta. And the square of this plus the square of this is going to be x squared plus y squared will be equal to the square of this plus the square of this, which is r squared, times cosine squared theta plus sine squared theta. So this is 1 every day. So what we're left with is just x squared plus y squared equals r squared times 1. So we know that r squared equals x squared plus y squared, which means I can just replace this with r squared. But how do I replace these? I'll have to replace these also, because we're now going from the rectangular coordinate system, we're beginning to move on, or we're not beginning, we're going to move to the polar coordinate system, which has r and theta as what they work with. This one works with x and y. So how do we change these so that what it's working on is not x, y, it is working on r and theta? We're now going to transform this integral into something in polar form. Now watch what I'm going to do. Let's start from the beginning. The boundaries we have here go from negative infinity to positive infinity. And for the y, it goes from negative infinity to positive infinity. Now imagine the rectangular coordinate system or your x and y plane. You notice that this will cover everything, both on the x and on the y. Now, if you want to cover everything when it comes to polar coordinates, then you have to go from 0 degrees all the way to 2 pi. So we could replace this with going from 0 to 2 pi. So this new boundaries will be from 0 to 2 pi because that's the farthest you can go. And as far as the y-axis, from negative to infinity, we can say, let this be r, which would be the value of r. And if you want to replace and you want r to cover everything, then you have to go from 0 to infinity. So we're going to have here from 0 to infinity. That's what we have. So just understand this replacement. Whenever you're switching from this to this, know the replacement. I don't want to get distracted. Let's just stay on this, okay? Now we go back here and replace this. It becomes e to the negative r squared. Okay, because we said this is r squared. Now, we need to change dx. Now, you cannot just change dx to dr or d theta and change dy to whatever you want to do. No, we can't do that. Okay, we want to change dx, dy. We want it to become dr, d theta. But these two are not exactly the same. They are similar but not the same. It's like saying something varies directly as another thing, but they're not exactly the same thing. So we can say, this is not true, okay? You can say this varies directly as this. But in order to make them the same, you have to multiply by a constant. Now, the idea of a constant is what we call the Jacobian. Okay, so whenever you're switching from this to this, you have to multiply this by the Jacobian of this function, which can be computed maybe in another video. It's a very simple computation, but what you get for the Jacobian of this transition is r. So every time you convert from the rectangular to the polar, you have to multiply by r when you replace dx dy by dr the theta. So dx dy is replaced by r dr the theta. That is what you must remember. Okay, let's move on. So this is going to be r dr d theta. And now we can easily integrate this. Can you see? Because the derivative of r squared is 2r, and there's r waiting for us here, and that means the computation is easy. So let's finish this. So like you know, my favorite u substitution is going to come in here, and let's see what I get from this. Now what I'm going to do is say let u be equal to negative r squared. And because this is a definite integral, it's always good for me to replace immediately so I don't forget. So I'm going to say when u is evaluated at 0, here, what am I going to get? That's going to be 0. Minus 0 squared is 0. But when u is evaluated at infinity, well, it's going to be minus infinity squared, which is minus infinity. So it means that my boundaries will change to 0 and negative infinity. Those are my two new boundaries. Do I want to switch? Because I'm evaluating, I don't care. I'm just going to leave it that way and plug it in when it's time. Not plug it in, take the limit, okay, for this one. But So here, that's what I have. Now let's find our du. Du will be negative 2r dr, so that negative 1/2 of du will be equal to r dr. So I can go here and replace r dr with negative 1/2 du, and then I write this as e to the u. So I'm going to have e to the u in the middle here, and I'm going to replace r dr with negative 1/2 du, but I'm going to put the du inside and put negative 1/2 on the outside. So this is going to be equal to negative 1/2 multiplied by e to the u evaluated from 0 to negative infinity. Okay. I cannot plug in negative infinity, so I shouldn't actually put this here. I should have written this as a limit. Let's box this up. This is going to be equal to, negative 1/2 times the limit as t goes to infinity, u evaluated from 0 to t, to negative t. Okay, so this is what I was supposed to write here, actually. Okay, let's finish this up. Negative 1/2 times the limit as t goes to infinity of, if you plug in negative t, it's going to be e to the negative t, which is 1 over e to the t minus e to the 0. Okay, so this is what we have. I've plugged in the two values, and e to the negative t, I've written it this way. This is negative 1/2 times, what is this limit? As t goes to infinity, this is going to go to 0. So this is 0 minus e to the 0 is 1. Oh, so what do we have? Minus 1/2 minus 1, that's going to be 1 over 2. So everything we've done gives us 1/2. So I'm going to go back to this line. Well, we're done with this calculation. I'm going to go back to this line and say, okay, this part on the inside is just 1/2. So we can continue and say that I squared is equal to the integral from 0 to 2 pi of what is inside here, which we said was 1/2 d theta. Isn't this so easy to do? See, the more complicated one is already gone. Now let's integrate this. If we integrate this, what do we have? We have this is equal to 1/2 of theta evaluated from 0 to 2 pi. Nice. And what does that give us? It gives us 1/2. Then you're going to be doing 2 pi minus, you put 0, that's going to be 0. Okay, this is equal to 1/2 of 2 pi, which is equal to pi. So we can say I squared is equal to pi, so that I is the square root of pi. Some people will say plus or minus, but we're talking about the area under the curve, and it's on top. Remember, it's supposed to be the area on top of the x-axis. Okay? And that's it. Never stop learning. Those who stop learning have stopped living. Bye-bye.